Fixing Newton's second law of motion by acceleration allocation by Arno-Vigen. Now, Newton's variable mass causes a 1 over m catastrophe. You see, Newton's second law of motion has acceleration equals force over mass, but we know that mass is variable. Now, I'm going to take a different approach, and I'm going to talk about the sum of the accelerations of particle A and particle B. Now, understand that in regular math, you would have them going in opposite directions or both matching directions, but in the frame of reference of one of them, those are a sum so that the overall works. But Newton, by its nature, causes a problem here, because both would have the same force, they're the interactive set, and by this rule you would have F over m1 over F plus F over m2. But that becomes the force times the mass of 2 plus the mass of 1 over the product m1, m2. At the right, that's a graph of this behavior. Now, on the x-axis is the mass, and on the y-axis is the sum of the particle accelerations, a1 plus a2. Now, look at that graph. There's a lot of problems with this graph. First, the two particles, by their nature, must both be on the graph. Also, sort of they're interactive in the way that if one moves on one way of the graph, it sort of has to balance by that product, m1, m2, with the other one moving opposite, so that mass is interactive inverse related to each other. So look at the red arrow. This graph passes through 2, not 1. So your interactive has this sort of warping. Now, that 2 was actually solved by Dirac's equation, but that's an error correction that's applied then manually, and then you go back and still use F over MA, over M1, or F over M2. And so Dirac's method is basically just trying to correct this. Okay? Now, there's also another one, so as the mass, say, of the electron moves out further, now it's still this graph, but I want that graph to go through 1 and then to attenuate out to 0 out at the far set, which sort of looks like that long curve to the right. But instead, that is slightly off, and that's called the anomalous moment. This is the G minus 2 over 2 correction to Dirac's equation, which is done via Nafe and Nelson's experiments that identified this, and then Landy's anomalous moment, and eventually the Feynman and Schwinger and Tomonaga QED findings. We're going to be able to correct that because we're going to go to first principles and change the to work in acceleration with a new version of Newton's second law of motion. Now, Newton's is sort of, I call this a catastrophe. And that's really just going back to what's called Rayleigh-Jeans catastrophe for the ultraviolet. Rayleigh-Jeans, in the closed container, the black box, had an ultraviolet catastrophe, and that is that it says the energy of a photon would continue forever, becoming infinitely strong. Now, that's not what the, of course, experiments discovered, and what eventually Planck solved at the start. Now, Planck solved this by a 1 over e to the x minus 1. But what is that e to the x? That e to the x is a 1 plus 1 over x to the 0 times 0 factorial, and then the 1 over x to the 1, 1 factorial, x to the 2, 2 factorial, x to the 3. But it has an extra 1 plus, and that's a gradient, sort of like a MetaGGA if you're looking at Purdue's DTF graph or ladder in density functional theory. So adding this 1 plus basically is a way for us to get a gradient where things aren't strictly inverse, but they're interactively inverse. They're limited. Now, I'm going to solve Newton's 1 over m. By a similar method, it's going to be 1 over 1 plus this ratio that we'll find for the position in field. Now, there are many current error corrections, as I said. There is localization, or LDA, in DFT, density functional theory. That changes equations by r to the 4/3. And this is important because I'm actually going to steal that part and it's going to go back into the equations that we're doing, that my result is, because it's a valid error correction, but if I put it back in Newton, we don't have to do it again. Similarly, we get Einstein's space-time curvature, basically in general relativity, and that sort of twists equations. They're saying twisting space-time, but they're really basically saying the results have some sort of a gradient on it, again, a gradient. And so I'm also going to say that general relativity is a function to fix Newton's second law of motion with a 1 over 1 plus some ratio, some scaling, which looks like r to the 4/3. And that will get you also this partition of general relativity, so we won't have to use that. Next, we've got this anomalous moment that I talked about with Landy and Weinberg and others of g minus 2 over 2. And that's approximately 1.0011. That tiny adjustment goes away when we fix Newton's second law. And in the results, we'll actually get an understanding of alpha, the fine structure constant. Now, to get these replacements, you need to look at the position in field. So when we talk about variable mass, how does it vary and why does it vary? And in part, this is the correct concept out of LDA, localization. And that is it changes by a field. And I'm going to go back to that r to the 4/3. Now, if we have charge, which is radial electrostatic force, the force is at 1 over distance squared, and the field is at 1 over distance cubed. Now, if we have hypercharge or magnetism, the force is at 1 over distance cubed, and the field at 1 over distance to the 4th. So now I have fields at 1 over distance to the 3rd and 1 over distance to the 4th. And the comparison of those two would be radius times the 4/3. I now have a concept for the replacement of that is our current error correction. So we're going to use these comparisons of charge versus omega elementary particle to figure out how this works. So now the other thing is that you have to have a scale. Once you are doing this, doing something to the 4/3 power, traditionally we've done electrostatic as 1 over distance cubed, but you can't do that to the 4/3 power. It's even tough to understand what the square is. Maybe the cube, because you can do the volume, but 1 over distance squared, it's not a box. So instead, what I'm going to do is I'm going to replace the distances in all exponent sections. This is the hemi-quantum rule, is that exponents must be base have base. So it becomes distance over distance base. And that is net dimensionless. It has distances in it, but it's distance over distance, so it's dimensionless, like the fine structure constant, which thereby can be at different exponents, but now you have a relationship that affects total strength that's effective. Now, what is that distance base? That distance base is the particle edge. It's the radius of the electron, or the radius of the proton. And I'm going to use the same codes because I just don't want to keep flipping between R sub E and R sub P. And there's some discussions about whether there's like 3 versions of R sub P out there, depending on which part in the literature. So I'm just going to use R sub E, and it works as R sub P as well. So when I do that, I'm going to do scaling based upon, what's at R sub P, and that's where the strength of a field is maximum. We don't know what goes on inside a particle, but afterwards, we're going to know exactly what it is thereafter, and it's not inside the particle anymore. It's going to follow the same curve from R sub E out to infinity by these exponent reduction ratios above. Now, there's additional things, because obviously if in the nucleus there's elements with heavier amounts, their count increases, we're going to have a scaling constant, S sub n, to address those other elements. But for now, mostly I'm going to do the hydrogen 1 proton and 1 electron simple example. Now, this understands the hemispherical model for the atomic model. And that is, it's not simply a sphere, but subshells are longitudinal rings. And that means that you get 1 in the extra things. And that means that first one appears, say the proton. If the electron is on one side, there may be, say, a poly pair on the other side 2x away. Now, these don't have, electron doesn't have this magnetic omega field and in its interaction, so it's missing 1/2 to the 3rd power. That's 1/8. And so you'll find that the net effect for that is the full to the nucleus plus the particle pair, so it's 7/8, 1 minus 2 to the 3rd, or 8/7 if you're doing the inverse, which we will do all the time. So we're replacing everything in e to x techniques with an acceleration allocation using this gradient like a MetaGGA in order to calculate it. So what is this hemispherical model? Well, that means that subshells are longitudinal rings, and better, those are starting from the poles. So subshell S is on the pole, and then that's 2 times 1 in each pole. Then 2 times 3 becomes subshell L's, 2 times 5, and such. And the sum of those, 1 plus 3 is 4, that's the square. 1 plus 3 plus 5 is 9, that's the square of 3. 1 plus 3 plus 5 plus 7 is 16, that's the square of 4. You're now back to, when you do this pairing, an orbital or poly pair is then a sphere, and we can apply the normal Gaussian distributions and such. So I replace quantum numbers with actual hemispherical numbers, hemi-quantum numbers. So the first number is the radial, that's the number of layers starting at 1. The inclination is the angle relative to the equator starting at 0. So it's inclination, and because it starts at the equator, I use the word inclination versus longitude. Officially, longitude starts at the equator, goes the other direction, so I'm using the word inclination. And then the latitudes is the electrons around the ring at the same distance and at the same angle, so they're a set with the same energies. And finally, there's the hemispherical number, which of course is the axis of symmetry, the axis of all magnetism, as pre-magnetism, and that's plus or minus 1/2. And it's plus or minus 1/2 because you're either in the right one or the left one, and it's the poly pair. Once the first electron is in, the second one wants to be as far away as possible, locked at 180 degrees, pi radians, and it is locked there by basic 3D engineering. So how does this position and field work? In reality, I've said that the maximum strength of all fields is at the particle edge, R sub E. It's going to get every bit of strength that it can, and now once it's left the particle, it must be continuous from r sub e to infinity. But there really are two positions that are important. The first one is obviously that full strength, so that would be, say, charge at r sub e. But in reality, the other one is, for the simplest one-to-one, is at the Bohr radius, where naturally one proton and one electron come to balance. So if you take Coulomb's constant, and I'm going to do it per particle, so it would be k e squared, and that being the charge square of the two particles involved as the constant, not k alone or not, it's very similar. HC alpha would be another version of that, but this is probably the best way to explain it. And so at that level, at a sub o distance, that's the equilibrium of these two forces, okay? And that would be the electrostatic, the charge would be radial electrostatic, and the hypercharge, or the magnetism, or what I would call extrastatic, has that, because it has that extra exponent in it, would be the offset. So the equilibrium is at AO for the simplest model. So how does acceleration allocation work? So instead of doing F over M1, I'm doing F times M1 over M1 plus M2, or position and field, using the rule of the last slide. And so you get basically two particles. One's 1, and that would be, say, the electron, and then the one would be 1836 times stronger, that would be the proton. So the first one, if I do the sum of the two accelerations, it would be 1836 over 1836 plus 1, and the second particle would be F over 1 over 1836 plus 1. But guess what? That becomes 1837 over 1837, and I now have conservation of force. And if I have conservation of force, everything after that, conservation of energy, and all the things that are challenging us in quantum theory, become naturally flowing from first principles. And as such, I've replaced 1 over m with what is a gradient, and it's an interactive inverse gradient between the two particles. So let's look at that. That inverse relationship then is that you've got a position in field. I'm running out of variables, so I'm going to call it PIF. Okay, and that PIF is going to be 1 over distance to the 4/3 as you do the ratio here of those two events. And so, but what I did before is that this applies, and I'm applying it now in the hemispherical coordinate system, in the cylindrical of, say, Bose's cylinder surface proof of quantum mechanics. So now when I do it, there are 4 dimensions: radial, inclination theta, latitude phi, and the z direction, which is the transfer, the x sub 0 if you're reading Einstein, and that is either plus 1/2 or minus 1/2 for the left hemisphere or the right hemisphere. Now, this applies only in the radial direction, and at that point, there is no interdimensional transfer. So in the fourth quantum number won't change at all, because when you get Pauli pairs, they're both filled, and you have a hemisphere becomes a sphere. And so this is based upon the logic of radial only. And because there's no inclination and there's no latitude, there is no transfer that causes Maxwell to apply. All right, let's... Now, in this sense, I'm basically going to take a new approach that incorporates a concept from Maxwell, but as I said, we're in radial only, so I don't have an interdimensional transfer. And that's how most people have been taught Maxwell equations. I'm going to say that in the radial direction, I have a mismatch of the fields. The position in the fields of the two of them are different. The proton is the dominant center, the one, by the way, and the electron is somewhere out, some reduction of that. And so this is what we're going to get. I've got to have, I can't do it by magnetism where it goes in another direction like a right-hand rule. Instead, it is done by acceleration allocation. The big secret to my process is that in the radial direction, the difference in the fields between the particles that are interacting is that they are balanced by an interactive inverse acceleration. So acceleration 1 times the position and field of 1 over 1 is the B field. And acceleration of 2 times the position and field of 2 is the B field also. And B field 1 plus B field 2 must equal 0. They have to balance. And so you get this interaction of them being interactive and opposite. And so because of this, you can... So in part, what I propose is that you've got an inverse relationship of to the 1/2 and to the minus 1/2. And if you take the derivative of 1/2, you get minus 1/2, so it becomes the inverse. And so the magic of a Gaussian distribution, if you remember, e to the 1/2 versus effectively your x versus the mean, gets you this. So particle 1 to particle 2 becomes inverse, but velocity becomes inverse to acceleration, and then particle 2 has acceleration to velocity, and you get this four-way 2x2, a symmetric SU2 matrix based upon these inverses flipping and flopping. So in the end, what is traditionally shown as hyperbolic sines, say e to the x plus e to the 1 over x, becomes the acceleration times the mass, which is the B field, over the sum of them, which is the gradient now. And so now the sum of those in that graph becomes magically 1 forever by this. And the B2, but now I have a way to know why the proton moves at a different speed than the electron. However, so effectively, now I have two equations and two variables. I'm trying to get the acceleration of 1 and the acceleration of 2, but I know that they have this inverse relationship, so I can put position and field over position and field, and that gets you one equation. But I also know that the sum of those is the force, because I'm effectively applying a gradient to that. And as a result, you get acceleration of 1 times 1 plus this position of field over position in field equals the force, and I get to replace that with the force per particle. So force divided by the mass of P1. So when you're taking the units of newtons, remember that I am reducing the kilograms out of that, so I'm getting meters per second squared per particle. So now I have an individual acceleration for each, and with that I have a complete replacement of the mass concept. So in then, I have a full replacement for mass. That is the concept of mass within the subatomic systems, particle level, doesn't help, or it's using the wrong calculation. It might work for full atoms, but even there it doesn't work. You see, it's an inverse interactive allocation between both objects. It doesn't work at the macro level, only at the extremes, when you have like Mercury orbiting a big, huge, monstrous sun, and there's a tiny 41 second difference in the period of that. Okay, but it does exist even at the macro level. Further, it is very clear that it occurs here at the subatomic level based upon the dominant proton position and field versus its radius, which would be the maximum value, which I presume to be all the same radius as the electron. So in the end, force over mass, the Newton concept, needs to get replaced. The acceleration of one particle in the radial direction is the force divided by, not by mass, but by the mass of the proton at rest, which obviously is the maximum mass that we can have, but then done by 1 plus this position in field of 1 over the position in field of 2. And with that, you basically get the calculations that fix mass at the gross level for the Mercury's orbit, as well as mass in all subatomic fields. Now I've added some notes here because we already do this in our error correction. You see, we have for the inverse something called localization. And it uses a formula called r to the 4/3. And it's applied on the inverse, so the 4/3 times the 3/4 effectively cancel each other out. Further, you have the 1 plus, and we have a process in density functional theory which applies a gradient, a sort of a gradient, that's what the GGA is, where it's sort of averaging but changing as it changes. So as the distance changes, obviously the position and field is going to change, and so this ratio will change. So you have to do an integral over various distances to get the true result for an operational event set within a subatomic particles. However, with this as the starting point, I've now combined into one equation the entire Purdue stack, and I'm able to apply it not waiting until we do density functional theory, but we can do it at every equation all the way back at the simple acceleration and force level and eliminate all those downstream problems. So let's test this out in the simplest program. We've got a proton and electron. That's a hydrogen atom. And the maximum is at the particle edge. And the dominant particle is the proton. So for our purposes here, I'm going to call that 1. And what's the ratio to the electron, which is way out in the field, and so it has less of a field. Okay, so if you take the equation at the Bohr radius and you use this 3/4, okay, calculation, and that's the AO, the Bohr hydrogen radius versus the particle edge, and you scale that at 3/4 to actual distance, you get a ratio of 1604. The full value is 18,778. And the square root of that is 137, which of course is the fine structure constant. And so this scaling of AO to RE by some W over V exponent is very common in physics. Now, because they're coming with Pauli pairs usually, and because the electron is going to have a scaling, and it's going to be, say, 2x off for the cube, which is the cube. So it's going to be 1 minus 1 over 2 cubed, which is 1/8, which leaves you 7/8. And of course, you have to apply the inverse of it for the distance out, for equilibrium. So by applying that equation at the back end, we're going to get 8/7 added here. So that's going to be 1833. And then if you apply the anomalous moment, again, we got to go back with this equation. I probably should have done it in the middle. You get 1836.163. That's pretty close to the ratio of the mass of the proton versus the mass of the electron. So it works in the simplest case. Now, what is important in that is also that effectively what I've done is I've eliminated that entire error correction state. So either I've eliminated localization and MetaGGA in a DFT, or I've eliminated what's called the anomalous moment as an error correction in other quantum materials, or in another case is probably eliminating basically special relativity from Einstein in another technique. These are all error correction takes. Now, so the anomalous moment is 0.00116, for example. All right, so now if I take here in the left column via 1 over m, the current method, and I take the force of the proton and the electron, I'm going to have the combination of those accelerations. So relative to the first one, the combination is, say, going away at 1837. 1 plus the 1836. Now, however, the current method requires me to adjust that by this anomalous moment. So I come to an effective calculation, the one that we observe, of 1835.025. And this is what the experimental results are, and everybody's been satisfied with this two-step procedure. However, if I apply the 1 plus the position and field scaling, I don't have to do that, because first I take the 1836, which is the force, and I simply allocate it to the proton and the electron. And that basically gets me a ratio where the sum of them is right back to 1836, the conservation of force, which gets you conservation of energy, and effectively the whole chain is perfect, so long as you use my second column, the acceleration allocation method. Now, at that point, what is the electron acceleration? Oh, it's 1835.152. Now, that's pretty close. In fact, it's off by 0.000065. Okay? When you apply it at the ratio of the cube, the exponent. And so what do? That's it. The adjustments basically disappear, or substantially less, and we'll go into other areas. So the final point here is that, in effect, I've done a whole bunch of things, but I did put in 2 additional steps. Actually, they would be in the Purdue ladder below this localization r to the 4/3, and thereby below also this MetaGGA, which is the 1 plus section of this allegation that gives you conservation of force. Now, typically, Rydberg, we know it works in general, it works for hydrogen-like elements, but then it fails miserably. And that's exactly because of this allocation. You see, if you took Rydberg and you wanted 4/3 pi r of some base cubed, and you wanted n protons in your nucleus, the top equation here shows you that you basically would take the n, put it inside at the cube root, which then of course is cubed again, and that thereby your factor of changing is n over to the 1/3. Yet that's not right. You see, instead you have to do this orbitals, this even odd sawtooth step function. And so I replace the n to the 1/3 of Rydberg with the averaging, that means the 1 over n in the bottom equation, of the odd counts at 8/7, the scaling we already showed, and the even counts at the n count over 2 to the cube root. And so it depends on what your count, and you get this difference between an odd count element and an even count element. And eventually, when you get to outer shells, there's another fine adjustment, which is covered in my books. Thank you.